Hello everyone, my name is Logan and welcome back to the lecture hall. Today we are covering section 3.10, linear approximation of our UCI Math 2A single variable calculus course. Jesus, that's a mouthful. Alright, so what is a linear approximation? Well, it's kind of exactly what it sounds like. It is an approximation with a line. It is to quote the book, it is approximating a point with a line. And what do I mean by this? Well, let's say we have our curve. This is our curve C. And we know that a point is right here, right? This is our point of interest, or whatever you want to call it. And as you can see, like, these are very close. As you go farther away, the line gets very far from this tangent line to the point, right? This is our tangent line. We'll call that T. As our tangent line gets closer to the point, it gets closer and closer to our point, right? So as you can see, this is very close to here, so that's approximately this. So you can use a tangent line at point A, f of A, or like y of A, whatever you want to call it, to approximate a point on the curve. So we have an equation, f of x is approximately equal to f of A plus f prime of A to x minus A, where A is a point of the tangent line and x is close to f of A. And this is called the linear approximation. So we get this L of x, the linear approximation of x, is equal to f of A plus f prime of A, x minus A. And you're like, okay, well, these are the same equations, but this is f of x is approximately equal to, and this says the linear approximation is equal to. And this is just because f of x is almost this, but it is the linear approximation of this. So that is what we have. And this is called the linearization. This L of x is the linearization of f at A. So you need to remember this formula. This is probably the most important formula for this section. Let's say we have a sine curve, right? You start here, start at the origin. Where does it start? It starts at 0, goes up, goes down, blah, blah, blah. But what if we take the limit as x approaches 0 of sine of x? Well, what is this going to be equal to? Well, we can kind of see, if we grab a different color marker, we see, okay, as it's coming in, it's following this, and then as we get very close to the origin, it almost makes the y equals x line, right? Our up one, rise over run one line, just y equals x, right? And this is when it's very close to x, right? Because if you were to look here, you see, okay, it's basically all at the origin. And it slowly drifts away as x gets farther from 0, but as the limit as x approaches 0 of sine of x, it's just equal to x. And we get this from our linear approximation. So this is an important little property to know, because it's one of those properties that a professor will put on the test for like 2 points or 3 points, and they just say, oh, you know, they give you sine of point, I don't know, 3286, and you're just like, I have no idea. But as you see, okay, it's getting close to 0. Oh, this just equals 0.3286, or whatever it may be. So this is just a good little thing to remember. Now onto the last topic of the lecture. Now onto the last topic of the lecture, differentials. If y equals f of x, where f is a differentiable function, then the differential, dx, is an independent variable, and dx can be given any real number. So this fancy r, this r with like a second thing, is means set of real numbers. So what is this saying? Well, it's saying we know the derivative of, let's just say y. The derivative is going to be dy dx, right? And this is equal to whatever our function may be. Whatever it is, it doesn't really matter. But what it's saying is dy is an independent variable, or dx is an independent variable and can be given any real number, because this will just output some sort of number at some point, right? And that's kind of arbitrary. Oh, some number at some point. But that's kind of what it is, because the derivative is finding your slope, right? And so your slope is a number. It's the rise over run, right? And so your dx is going to be your run, and your dy is your rise, right? And then, so dy is the amount that the tangent line rises or falls, right? And so dx is going to be how far the tangent line runs, whether it runs this way or that way or whatever it may be. It's how much the change in x is. And then now we get a equation, and it just says the change in y is equal to f of x plus the change in x minus f of x. And so what is the change in y? And change in y represents the amount the curve rises or falls when x changes by dx. So it's kind of like, well, what? Well, this change in x is also dx, and it's basically just saying, well, y changes by this much when our function changes by, our output changes by this much when our input changes by this much inside the function. So this is a differential. It's obvious. Well, every topic I cover in this lecture series is important, but I wouldn't say it's the number one thing you need to take away from Math 2A, but I just remember it. This is all for the lecture part of the video. Let's transition into some practice problems. Wait, before the transition. I didn't do something properly. So, if we had, I wrote the differential kind of weird. We had y is equal to f of x, right? And if we were to take the derivative of it, we get dy dx is equal to f prime of x, correct? And so what this is saying, dy is equal to f prime of x dx. And that is where I came from. Dx can take any real number, because this is multiplied by our slope, and that will give us the dy, which is our change in how much it rises and falls. Okay, now you can transition. Now on to the practice problems. We're going to be doing number 3 and number 19. This says, find the linearization function at a. Well, what is our linearization function? L of x is equal to f of a plus f prime of a times x minus a. Okay, so then, well, what is our f of x? We know f of x is equal to square root of x. What is f of a? Let's just start doing it piece by piece. What is f of a? Well, a is 4, so the square root of 4 is 2, plus f prime of a. Oh, well, we need to solve for that, but then we know this is x minus 2, right? So we need to solve for f prime of a. F prime of x is equal to square root x. So then we do, f of x is equal to square root x. Then we dx on both sides, right? and we use power rule, and we get that it is equal to f prime of x is equal to 1 over 2 root x. And how do we get that? Because this is equal to x to the 1/2, and then we do power rule, so minus 1, and we bring out the 1/2 in front, and we get that. And then we plug in 4 again, and we get, okay, so f prime of a is equal to f prime of 2, which is equal to 1/2 square root, sorry, it should be f prime of 4, which is equal to 1/2 square root 4, which is just equal to 1 over 2 times 2, which is equal to 1/4. Okay, perfect. And then we was like, oh, f prime of a is just 1/4, so we can erase this. We get 1/4, and we find the linearization for the function f of x is equal to the square root of x at a equals 4 is equal to 2 plus 1/4 times x minus 2. And that's how you do these. They're really simple. You just kind of just plug and chug. Now on to number 19. What does it say? Compute delta y and dy for the given values of x and dx, which is equal to delta x. Okay, what does this say? Well, we have two equations, right? From right before that transition, I said dy is equal to f prime of x dx, right? And then we also have that our change in x, or change in y, is equal to f of x plus change of x minus f of x. Okay, that's not too bad. So we just have to solve for these. Okay, first one. Let's solve for dy, which is equal to f prime of x dx, where our change in x, which is equal to our dx, is 0.5. Okay, so what is f prime of x is equal to power rule, 2x minus 4. Okay, that's not too bad. And then it's x equals 3. So f prime of 3 is equal to 6 minus 4. Okay, so then our dy is equal to 6 minus 4, which is equal to 2. So it's equal to 2 times dx, which is equal to delta x, which is equal to 0.5, which is equal to 2 times 1/2, which is equal just to 1. Okay, so that is our differential of y. Y is equal to x squared minus 4x at x equals 3, with dx being equal to 0.5. Now, we have to find our delta y. What's our delta y? Well, this is equal to f of x plus delta x, which is just equal to f of 3.5 minus f of 3. Okay? And so that is equal to 3.5 squared minus 4 times 3.5 minus 3 squared plus 3 times 4. Where did I say, okay, minus, plus, well, this is a minus here, so then this is a minus this, so this turns this to a plus. And now, movie magic, I'm going to come up with the answer because I can't do 3.5 squared in my head. Alright, so we get that it is 3.5 squared minus 4 times 3.5 minus 3 squared plus 3 times 4, and that's just 12.25 minus 14 minus 9 plus 12, and that just equals 1.25. And so that is going to be our delta y in this case. And we see, oh, well, these are different. Is that okay? That's completely okay. Because they're really different equations, right? Because this actually, you find the slope, right? And then you know your dx is 0.5, and then you find your dy. But this one is different because you don't actually use your slope. You just add your delta x inside the x and just subtract it from your other x. In reality, this is going to be a lot more accurate than this one, right? So, that is all for the video today. That's all I wanted to cover. Again, my name was Logan. Thanks for watching. Have a great day. Let's go, anteaters. Yes, hot.